This video, along with all course content, including laboratory and hands-on activities, were developed by Andrew S. Heinz, PhD, and are copyrighted 2016, 2018, and 2020. All rights reserved. The student's course handbook serves as a guide and as a resource to the student throughout the course. It contains the sample problems done during class, laboratory activities, and practice problems to develop knowledge outside of the classroom. It is available on Amazon. We all ready? A little light tonight, but I guess you guys all had big tests today. ACTs, your trial for life, right? Make or break whether or not you get into college or not. Nah, you'll be fine. Did everything go well? I guess nobody's going to say no. Fair enough. Hey. Hey. All right, guys, so remind me what we talked about last week, because I forget. Actually, it was 2 weeks ago. 2 weeks ago. What did we talk about?
Google Sheets.
What's that? Spreadsheets?
Google Sheets,
yeah. Yeah, so, Google Sheets, yeah, that's fair. Yeah, so the big takeaway from last time was that we looked at units and conversions first, is what we started with, and you guys were all bored because you guys are all masters of that, which is super awesome, right? But then we went into finishing the second half of our rocket problem, in which we used a spreadsheet to solve the problem. But what did we use the spreadsheet to actually do? What were we functionally doing with the spreadsheet, Kate? Calculations, okay. So what we call that is building a model, right? We built a model in which we modeled shooting our rocket. That's what we were doing, right? Created a computer model of it. I mean, it was in a spreadsheet and it wasn't super fancy with lines of code and stuff like that, but that's what we did, is we created a computer model, right? And what was really cool about that is we could go through and we could actually change the parameters. So once we built our framework, we could go say our rocket's larger, our rocket's smaller, it needs to go higher, it doesn't need to go as high, and we could go change the parameters. Okay, we could use ethanol as a fuel instead of, what was it, super awesome, amazing jet fuel or whatever we came up with, right? Okay, so hey DT. So that's what we did last week. What was everybody's big takeaway from last week? Or 2 weeks ago, I guess. What was one thing you remember from last week? That it was super boring? We did spreadsheets? Yeah, because even I screwed it up, didn't I? I screwed up that one column, right? Yeah, and I mean, it's all formulas, it's all just math, right? But all we were doing in that spreadsheet functionally was we were putting in the real world formulas that we had developed on the chalkboard or the whiteboard the week before, right? So we were taking what we talk about in this class and we were actually putting it to real use as engineers, right? So you guys were actually doing a real cool engineering problem last week, okay? All right, tonight we were talking about engineering mechanics. So before we get into that, I want to talk about a couple disciplines like I talked about first. But first, let me ask you guys a question. What is engineering mechanics? Does anybody know what that is? What do you think it is, Aditi?
Maybe working with machines.
With machines? Okay, fair enough. What do you think, River?
So I guess like it could also be like 3D printing or like wood cutting, CAD.
Okay, good guesses. All right. So we'll see when we get there. We'll talk about engineering mechanics, but it's going to be way simpler than you guys think. All right, so first, I want to talk about civil engineering, because civil engineering is kind of like, when you think of engineering mechanics, you basically think civil engineering, right? Things standing up, buildings standing up, doing bridges. Who here, let me see a quick show of hands, who here wants to be my civil engineers? I think she's late. She thinks she said she wasn't going to come. All right, fair enough. So, all right, so civvy, as we call them, civil engineers are concerned with the development of public infrastructure and services, right? They're basically what you would think a civil engineer does. They do your roads, they make buildings stand up, they make bridges stand up. But civil engineer is actually a huge range. I actually did an internship when I was in high school. Well, basically I did a job shadow. I followed him around for a couple days. But he did HVAC systems, right? Sounds very boring, but that air cooling system, getting air from, right, the heat that you guys need in this room, although the room is usually pretty hot, this room is. But getting it from the central boiler system, getting that to here, that's an engineering problem, right? If you don't do that properly, what happens to the part in the middle of the school? It gets super warm. The rooms outside don't, right? You have it in your home, right? So HVAC may not seem super sexy to you guys, but it's something that needs done, right? When you're sitting in a parking lot and it's raining, where does all the water go? It just sits there, pulls up, we'll drown? No, where's it go?
Down the drain.
Down a drain, right? So if you're standing in a parking lot and it's in order for that water to drain, it must slope, right? So some engineer figured out how to make that slope, how to big size the drain so that it wouldn't flow, right? Who lives by a creek? There's a creek near my house, Bethany Creek. Sometimes when it rains too high, what happens? It floods. Or when it rains too hard, what happens? It floods, right? Have you ever seen your creek flood?
Yeah.
Okay. It probably floods because why?
There's too much water.
There's too much water, and yes, there's too much water, but what's the problem with getting that water out?
It doesn't have anywhere to go.
It doesn't have anywhere to go, right? So let's say you're now a city engineer and you're deciding how to drain the water out of a city. If you didn't size your culverts correctly or your ditches correctly or whatever, you could have a serious problem that could seriously impact a lot of people, right? And then there's, of course, the gross side of it, which is managing waste and all of that, right? The civil engineers are also heavily involved in designing factories, designing industrial sites to make sure that not only stuff gets out properly, but some things can't get out, right? Like if there's a chemical spill or something like that, we want to make sure stuff can't get out. Environmental engineers are involved in that as well, okay? So aside from just the roads and highways, buildings, tunnels, dams, and other stuff that you would think about, they do what we also just talked about. And again, like I said, if you've ever wondered why a road slopes towards the edge, any runners in here? Got to have a couple runners, right? Right. What's the problem when you go out running on the roads? Yeah, it's sloped, right? Your left leg gets a little longer than your right leg if you're running on the proper side of the road. Then you have to flip, right? It's a problem if you run the same direction on the track all the time, right? Yeah, it's the same type of thing, right? You want the road to slope toward the edge. If the road sloped toward the middle, what would happen? Hydroplaning, right? I mean, it's pretty simple stuff, but someone needs to design this, someone needs to follow grades, someone needs to follow codes, right? Again, we used the example last week of rise over run of a handicap ramp, right? If your handicap ramp's like this, somebody's gonna have real fun going out, but they're gonna have a hard time going in, right? So it needs to be proper like this, and someone has to enforce those codes. Right, so Civ is by far the most diverse, and that's because it's also the oldest, right? If you really think about it, we talked about that kind of originally. Engineering itself really kind of developed, like, I don't know, back in the Roman times. Before that's kind of when you think of it, of people who built the buildings, right? The aqueducts, whatever. That was all engineering. So structural engineers focus on the design of buildings and large structures. That makes sense, right? They want to make sure that the buildings that we're in stay not moving. Transportation engineers, your traffic engineers. I would love, if any of your parents are a traffic engineer, I haven't had one yet, but I would love to get a traffic engineer to talk to us. I would find that just immensely fascinating to try to figure out the differences between theoretical design and actual people driving. I would love to just have a conversation about that. We have water resources engineers concerned with drainage and then the collection and management of our water. Geotechnical engineers, somebody needs to come in and say, all right, we're about to build a skyscraper. How far do I need to drive the piles down? Right? Do I need to go all the way to bedrock? How much weight can this soil support? Someone needs to come in and figure that out. You can't build a skyscraper on quicksand. It's going to be a bad time. Urban planning engineers, also municipal engineers, are concerned with the design and layout of stuff, right? Not only is that, all right, we have so many single family housings, now we need so many apartments in that area, but they also need to think about how many, think about it. How many people can I have in a square density? How much waste are they going to generate? How much water are they going to need? How much power are they going to need? How much electric? Like, those are real things that if you don't size that correctly, like in some other, like, we're very fortunate that we have what we do have in this country. There are other countries that have so many people in a city that they have rolling brownouts. They intentionally shut off parts of the city at certain times so that everyone can have power at some point during the day, right? If you don't do it properly, that's what we end up with, okay? Then we have construction engineers. This is actually a really cool field. Construction engineers serve as the gap between the engineering design, they serve as the bridge, that is, over the gap between engineering design and the actual people out building and making the decisions on the fly, right? Because again, you guys know, right? You guys can have a perfect plan, and then when you get out into the field, things may not go the right way. So the construction engineer deals not only with the planning originally, but also the implementation. Right? It's actually a very fascinating field. All right, so professional profile. So this is my friend Raisa. She is a PE. Does anybody know what a PE is?
Physical education.
Physical education, no. So, well, I mean, that's true. But for engineering, it's the professional engineer. So what you will do, so if you go to get your engineering degree, you will have the opportunity to take what's called your FE, which is your Fundamentals of Engineering. Usually that's offered, well, it's offered around the years, but usually what you'll do is you'll sit for it your senior year. It really is, I think it's an 8-hour test. I think it's 2 4-hour sessions. The first 4 hour is like general engineering principles, and then the second 4 hours is specific to your field. Then after you get your FE, you spend so many years and, well, you spend so many hours working under a licensed PE, and then you can sit for the professional engineering test and you can become a professional engineer. So not all engineers are professional engineers. It's an actual so I am not a PE. It's an actual certification that's used for people specifically that work with, like electrical engineers will have it, civil engineers will have it, people who are generally working with the government and have to sign off on like public utilities projects, right? So if you're going to say certified that this bridge will stand up, you need to be a professional engineer to actually put literally your stamp on it, right? You'll put a stamp on it saying, I as a PE certify that this bridge will not fall down. Or I as a PE certified that this power system will not catch fire when we run so many volts through it, right? So it's just a certification that essentially shows you know what you're talking about. Now again, not all engineers have the professional engineering license, and actually there was a big lawsuit in Oregon a couple years ago you guys may have heard of, where Oregon was saying you couldn't call yourself an engineer if you didn't have the PE license, and there was a group that sued them and they won, right? So you can call yourself an engineer if you don't have a PE license according to the state of Oregon. They won because they said that Oregon doesn't own the right to the word engineer. Anyway, so what Raisa is, so this is actually since moved on. So she's a project manager at NRG Renewables. This is actually back when she was working with SunPower. But so she has her BS in civil engineering from University of Wisconsin-Madison, which is actually also where my wife went. She'll be here later. But she's a civil engineer, and instead of reading all that long stuff that she talked about, I just wanted to show you what she's worked on. So I'm going to hit the lights here real quick. All right, so this is one of the projects she's more proud of. So this is the Antelope Valley Solar Ranch. This is located just north of Los Angeles, right? There's Vegas, there's LA, there's San Francisco, just to put it in perspective. I have this here. You can see that there's all these little things out here, right? All these little weird things that don't quite look like farmers' fields. If you zoom in more, you see that it's just a whole bunch of solar panels. Okay, so I'm going to turn the lights back on. All right, so that in of itself means, so this is actually the largest, still is the largest solar panel farm in the country, and I think it was at one point the world. I don't think it is anymore. It's 765, I think somewhere in that range. So this may not seem super exciting, but I want you to think about not only the actual construction of something like this and worrying about what happens when you literally take that much farmland and turn it into not farmland. Again, you have to worry about the drainage concerns. You have to worry about all that other stuff. But you actually have to have power distribution systems to collect all this, store it, and transmit it back to the hungry, hungry, hungry city down here, right? Because it's obviously you don't want it in downtown. That makes for a really poor park. Right? Your dog might be okay peeing on it, but it's really bad to throw a Frisbee, okay? So there's tons of engineering that goes into this, and she was very proud of this project. It took them a long time to get it. So again, it's not, right, civil engineering is not necessarily the most exciting field from a, tell your friends about it standpoint, but it's a very, very challenging field and is exceedingly necessary for our continuation, right? You need no less, or potentially even more so than some of the biomedical fields and stuff like that, right? Solving disease, obviously super important for us, especially right now with this whole corona thing going around, but we also need basic utilities, otherwise there's no point in solving that disease because we're all dead anyway. Okay? All right, so what you might actually care about, civil engineer median pay, and this is not starting, but median pay for a civil engineer, and that's for someone who's classified as a civil engineer non-manager. And this data comes from the U.S. Bureau of Labor Statistics. $82,200 per year is the average salary, which comes out to about $39.53 per hour. Now, you will always see hours per like this because they normalize it to a 40-hour work week. You guys all know, we've already talked about it, you're not going to be working 40-hour work weeks when you're an engineer. It's just not the way it is. What you don't ever want to do as an engineer is divide it by hour worked, because it always makes you sad, right? You always work more hours, just go off your base salary, okay? So the cool thing about this is the typical entry-level education is a bachelor's, right? That's not true across the board, that's true for most. But you can have a bachelor's, and job outlook for 2014 through 2024, that's their estimate, is that it's going to grow at about 8%. About 8% new jobs, and there will be roughly 23,000 more jobs over that period, is what they estimate. So that's pretty good. So you have, again, 82 per year is pretty decent pay, guys, for a bachelor's degree. Now, of course, remember, that's not starting. Yes?
Are there specific locations or cities that are...
No, that's one of, well, I mean, more growing cities are going to be more apt for that. That's a fair point. But one of the cool things about civil engineering is everybody needs a civil engineer, right? Civil engineers are needed everywhere all the time, because you not only need, it's not just, obviously you need more if you're building, but you also need people who can maintain projects, worry about not renewing, what am I trying to say? When you buy a house and flip it, you are remodeling, thank you, remodel type projects, stuff like that, right? Civil engineers are actually in high demand, and they actually have a relatively consistent job scope. All right, any questions about, oh yeah, sorry, real quick on civies. So these are the top 5, because I know you guys are always concerned about the schools to look at. The top 5 undergrad schools, this is as per 2018, the best undergraduate schools. This is for undergrad only. UC Berkeley, Georgia Tech, UIUC, that's University Illinois Urbana-Champaign. I usually just call it UIUC. We have UTA, which is UT Austin, and then MIT. So MIT is number 5. Okay, you'll see MIT at the top of these lists quite frequently, which should not be a surprise to anybody. All right, next let's talk about mechanical engineering. See my mechanical engineers in the house. 1? All right, so I'm gonna talk to you then, right? Just you and me. All right, so mechies design and manufacture machines of all types, machines and devices of all types. Okay, mechies work on power generating devices such as generators and stuff like that, but they also work on power consuming devices, right? So not only do they work on the machines that make our power, but they also work on stuff that consume power, right? In short, basically, mechanical engineers basically do everything in the industry in terms of machines, okay? And they also work on maintaining them. So mechanical engineer, the 2016 median pay was $84,190, so roughly $84,000, a little higher than your average civil engineer, but basically on par. The job outlook for mechanical engineers is a little higher. It's 9%, but again, it's right in that range. And again, you're looking at about 25,000 more jobs expected. Okay, so again, a pretty good field to be looking at if you're looking for employment. Any questions on mechanical engineering? Oh, again, I forgot the schools. So best mechanical engineering school is MIT, followed by Stanford, followed by Georgia Tech, and then University of Michigan, and UC Berkeley pull in number 5 if you want to go down to UC Berkeley and hang out with all the hippies. All right. All right, now quick, any questions about civil engineering or mechanical engineering? So we only had 1 in here who wants to be any of the above, huh? All right, fair enough. All right, so let's go into today's lecture, engineering mechanics. So engineering mechanics is dealing with machines. Is that what we decided? Yeah, so that's actually not true. Okay, so what engineering mechanics is working with things that stand up or working with things that move, right? Mechanics, what's mechanics itself? What's mechanics?
Rules and practices that make something function.
The rules and practices make something function. Yeah, and it's more so what makes things move, right? Mechanics is really just fancy physics. That's really all it boils down to. And that's why before we get into it, I want to talk about a quick trig review, right? I hate math. Math's the worst. I'm never going to use this. When am I ever going to use this? I don't need to go to the store and do trig, right? Well, welcome to engineering. Trig is actually probably one of the more important ones you're going to take. Trig is actually really awesome. So everybody remind me. Sine, SOHCAHTOA, right? SOHCAHTOA. I've heard somebody else say something different, right? SOHCAHTOA, is there another word that you guys use to remember this? It's just SOHCAHTOA. You guys are all on board with that? All right. So sine is opposite over hypotenuse. Cosine is adjacent over hypotenuse. And tangent is, right? SOHCAHTOA. Oh, touchdown. We all got it. All right. So again, just to make it clear, when we say opposite, we mean the opposite of the angle that we're looking at. If I move the angle over here, would this still be opposite? This would be opposite. This would be adjacent. Does my hypotenuse change? No, because why? Because that's the definition of hypotenuse, right? Fair enough. All right, very good. All right, so mechanics is the study of a rigid body's motion or lack thereof when a force is applied. What do I mean, Andrew, by a rigid body?
It's stiff.
It's stiff? All right, so it's like me at the gym, like, oh, right? Super hard, oh. No, what do I mean by a rigid body? It's stiff? So you're right, it's stiff, but what's the more important thing about it being stiff? It doesn't collapse. Good start. Good start. Tom, what do you think? How about I ask you this question? What makes a rigid body different than a fluid? Consistent in what? In properties. It's consistent in its size and shape, right? So you were there, right? So a rigid body, right, is something that we can, it's a theoretical construct. Obviously, we know that anything, no matter how hard it is, will still act and react when you put a force on it. It'll indent some microscopic amount, right? But the idea is that if I push on you, you're going to keep your same shape, right? Which, again, is not true. You're going to dent a little bit, right? But we treat it as the same body. And what's important about that is that we treat every point within that body as being the same distance. Right? So if I were to say I have a ball and there are, let's say, 10,000 molecules in that ball that each denoted a point. Each one of those points would stay in the same location relative to the others no matter what happens to that object. The object itself may move, that group of molecules may move, that group of points may move, but they're all going to keep the same location relative to each other. Does that make sense? Perfect. So when we talk about this body in mechanics, it can either be moving or at rest. And before we actually talk about that more, can somebody remind me one more time what the equation for force is? F equals ma, and what's m stand for? And what's a stand for? Acceleration. Good. So now here's the trick question. If a equals 0, if acceleration equals 0, what is my applied force? What is it? 0? Yes, that's correct, right? By definition. Okay? So engineering mechanics is the application of mechanics to solving real-world problems. In other words, like I said earlier, it's fancy physics applied to real-world problems. Okay? So there's two groups of mechanics study, and you'll actually take mechanics. Well, the majority of you will take mechanics your first year. It's usually second semester, first year, and then second semester, first year, and first semester, second year is a lot of the way it works. Some will take it first and second semester, first year. But it'll always generally be split up with statics and dynamics. Statics is the study of bodies that are in equilibrium. If I say something is in equilibrium, what do I mean?
It's equal.
It's equal?
Well, like the ratio is balanced.
Okay, what do I mean?
All of the forces being applied on the object balance out.
All right, all the forces being applied on the object balance out. What does that mean? What does that mean to my acceleration?
It is 0, but
Acceleration 0.
but it can still be moved.
And I heard it back there. I heard from Tom. What'd you say? Correct. It's a uniform velocity. But here's the trick question. Does that velocity, Eva, does that velocity have to be 0? No? Yes. That velocity does not have to be 0, right? And that's why we say in equilibrium it does not, it is moving or at rest. It does not have to be, right? As long as the forces are balanced, forces or net forces are 0, it can keep moving or it can keep not moving. And hopefully in the cases of our buildings that we're trying to get stand up, they're going to be not moving, right? Okay, but if you wanted to put something in orbit, is the space shuttle, is the space station in orbit, is it static or dynamic? That's actually a trick question because we haven't got to vectors yet, but what's one of the definitions of a vector? Both direction and magnitude, right? And if it's going around in orbit, it's actually changing in direction, right? Okay. So that's a trick question, Brett. All right, and then dynamics is, of course, the exact opposite of that, which is when your forces aren't balanced. That's when, right, that's the fun part of physics. That's when you're looking at cars speeding up, you're knocking stuff off the table and seeing how long it takes to hit the ground, right? That's what you guys did in physics, or well, you guys have all done physics, right? Nobody's here not done physics, right? Right. All right, so vectors, like we just so summly summed up, right? So in mechanics, there are two different types of quantities. There's a scalar. Scalar are the normal numbers we deal with, right? It's like 2. All right, 2 is a scalar. But, and well, we need to have units on there, right? 2 meters, but it doesn't specify anything, right? If I'm like, Kate, go 2 meters, that doesn't give her a lot of information. But if I go 2 meters in that direction, I just sent her on a vector. Okay? So you guys have all dealt with vectors in math class, right? I think that's usually geometry still freshman year? For some of you, ish. All right, but usually by second year, you guys have dealt with vectors, right? Probably even dealt with them some in like middle school, right? Like if a plane's going like this and it's getting blown by the wind, which way directions the plane go, right? That's what we're all talking about. Okay? So a vector quantity has both a direction and a magnitude, and thus vectors require more than one number to completely describe them. Why? Because it needs to have direction and a magnitude. Okay, perfect. So examples of vectors are acceleration, displacement, not distance, displacement, right? That's what the difference of what I was picking on Kate about, right? If I say go 2 meters, that's a distance. If I say go 2 meters that way, that's a displacement, right? Force, obviously, which is what we're going to talk about, and velocity. All right, so that all comes down to drawing our vector diagram, right? What is from a functional standpoint, what is a vector for us? It's really just a line on a piece of paper, right? That's really all it is for us in terms of what we've dealt with it so far, okay? But a vector quantity is represented by a vector diagram as shown, okay? So vector v, and we draw the little line over top of it because that's just the way we do it to denote a vector versus a scalar. So vector v is indicated by a line segment, this guy, with an arrowhead to indicate the specified direction. And then we also put in an angle somewhat from some reference point, right? In this case, and normally we use the ground. But if we were doing, let's say, a force on a building, maybe it's not the ground, maybe it's relative to the building. Right? In the case of our airplane flying through the air, we're not using the ground, we're using the wind on the airplane's original trajectory. Right? Okay? Any questions there? Perfect. Right. So what we're going to do is, and did you guys break down in component vectors? Have you done that as well? This is another one of those activities that fundamentally seems silly until you start to apply it and realize why it matters. Okay? So this vector that we drew, this red guy, here's our vector, and he's going off in this direction. What we want to do to fully describe this guy is we want to break him down in 2 components. So if you imagine this is on a graph, this guy has a y component going this direction, and he has an x component going in this direction. So what we're basically doing for these components is we're forming 2 vectors that we can then use to describe our primary vector. And it's the combination of these 2 together that describe our primary vector. Or, in more particular use of how we're going to use it, this primary vector has both of these components. And why this matters is, well, that's the practice problem. All right, but the point is, why this matters is we can actually start combining vectors. And when we start laying vectors in on end, it becomes, instead of going here, 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 and trying to track it, what you fundamentally want to do is you want to break it all down to the components, add the components up, and then we get one final vector. Okay? So, again, we have our angle here, right? And then this is a 90-degree angle, so what would this angle be? 90 minus theta, right? Right, remember this is guys theta. Okay? So if we let the angle between the vector and the x component equal theta, you get these formulas here, right? Where we get that the total value is vx squared plus vy squared rooted. The x component is v cosine of theta. The y component is v sine theta. And then you can get the angle itself if, let's say, the angle is undefined and you have the vectors. You can get the angle by using the inverse tangent of y over x. That comes up basically never, right, for functionally how we're going to use it. But I just want to make sure that that equation's up there for you guys to have. Okay, so are there any questions on this? All right, so again, if I have a vector going off in any direction, I can break it up into two components by doing what? By doing what?
You separate into an x component and y component, so you can separate.
Yeah, perfect. And how would I calculate the x component up there?
The cosine of theta.
Yeah, times the length of the vector, right? And how would I get the y component? By doing the same thing, except with y. Yeah, perfect. All right, so if we could please practice this by going to vector component, which I forget which page that's on. That one right there, yep. So that is on page 9, please. So the magnitude of vector A is 100 units, and it's 30 degrees from the horizontal. Please find the x component and the y component of this vector. All right, we all about got it? Who's got an answer for me? All right, what do you got?
For which one?
For both.
I got opposite is 50 and Jason is 86.6.
All right, so I got 50 root 3 and 50, which comes out to 50 root 3, because I'm lazy and I didn't multiply it out, right? But that's fair, and 50. And what does 50 root 3 come out to? 86.6. Nicely done. All right, but yeah, so again, we know there's a root 3 over 2 there for the cosine, right? So I just kept it simple, so 50 root 3, and then 50. Okay, nice and simple. All right, hopefully that didn't blow up anybody's world there. I know you guys have probably already done this a ton. All right, so that brings us to the vector addition. All right, so in this case, if we have two vectors that we want to look at, like the example I already used of a plane flying and the wind blowing that plane, instead of trying to figure out how it all works together, what we do is we actually set them end on end and then draw this red line in between them, which represents our vector, and that's what we call our resultant vector. So this guy here is our resultant vector r. Okay? Adding them together by is essentially just putting them head to head. And what we're fundamentally doing there is we're adding the components in there. Okay? So in this case, right, what we've done is, so again, remember we're looking at vector A here and vector B here. And if we add the components of that, we get A, which is this super tall guy, but he doesn't go very far. But then we have the wind, which is blowing him over this way, but he doesn't have as much of a y component. And then we box it out just like we did before, and we end up with our r component. And the resultant x component is just the sum of ax and bx. And the resultant y component is just the sum of ay and by. Okay, so what we then do, right, so what you guys just did in your example problem was you broke a vector down into x and y. So in this case, what we do is we just break both of our vectors down into their x and y's, add them up, and then using trig, find our new resultant. Simple enough? Yes? No? Okay, cool. All right. So let's talk free body diagrams. So a free body diagram, what we do is we use to show the relative magnitude and direction of all forces acting on an object. Because remember, that's what we functionally care about in what we're looking at, are the forces acting on our rigid body. Okay? So in this case, what I have is I have this ball here that's sitting, this is a horribly drawn picture of a ball sitting in a V, right? So it'd be something like this. Simple enough? So what are the forces? I mean, it's already drawn up there. But let's think about the forces that are actually acting on this ball, for lack of a better term. What's the first and foremost one? Gravity, right? So we know gravity is pulling it down, but every force, if this thing's not moving, every force has an equal and opposite force that's applied, right? So I have to have some sort of force keeping it in place. Now what's interesting here is because these are slanted, I don't just, right, if it was laying against the floor, I'd have a force down and a force back up, right? Everybody's happy. But these are slanted, so I have a force from the board pushing in this direction and a force from the board pushing in this direction. So talk to me about component vectors here, yeah? So the force of gravity is straight down. So let's call that our y direction, no problem. So what does the sum of both of the board forces have to equal? It has to equal gravity. Otherwise, what would happen to our ball? It would move. Well, or it would fly. Yeah, it would move in either direction, right? It's either going to bust it, right? If they are not strong enough to hold it, it's going to bust through our V and fall to the floor. Or if for some reason there's a force or something there, it'll make it go up in the air, right? So in order for it to stay firm, net force has to equal. You tired of me saying that yet? Yeah, we're going to keep pounding that in, okay? Furthermore, the force from the boards have to be equivalent. Otherwise, what would happen? It'd move one direction or the other. Okay? So very kind of stupid looking at an example like this, right? But now let's think about this on a building that's standing up or a bridge, right? You want to be on a bridge that has more force coming from the wind than it does from the ground holding it in place? The answer is, I don't think so. I see some of you smiling. I hope not. So, all right. So if we could go then to page, I think it is the next one. It should be page 10. Oh, page 10 here. All right. So this is the type of problem that you're going to see a lot of in your statics course, right? What this is it's a weight hanging in some fashion from some subset of strings. Okay, so let's talk through this problem real quick. First off, I want to point out that this is a 20 Newton weight, which means what?
The total force of the strings has to be 10 newtons.
Well, that's true. 20 newtons up. Yeah. But what I mean here is I didn't call this 20 kilograms, which means you don't have to calculate the force. It's a 20 Newton weight, which means that is actually the weight, right? It's not a mass that you then have to find the weight for. So that's 20 newtons is actually the weight. So I'm not asking you to go through and do the basic physics. I'm trying to shortcut the problem. Okay? But as he said, that's correct, right? So fundamentally, we know that we have a downward force of what? 20 newtons, which means that in order to keep this thing from moving, it has to have an upward force of what? 20 newtons, right? That part's simple. The hard part now is figuring out if I want to know what the tension on each one of these cords is, meaning the force on each one of the resultant force on each one of those, what do I have to know?
The length of one of the sides.
Okay. Do I though?
No.
Yeah, because I know, again, so what I know now, because we know that the upward force has to be what again? 20 newtons. I now know one side of my triangle, don't I? Yeah, so let's walk through this one together. Okay, so get your pencils out and we'll walk through this one together. All right, so let's start with our free body diagram. So what we have is this. We have a vector in the downward direction that is 20 newtons. And then we have two vectors keeping it in place. One, remember our geometry, right, or geometry? If this is 60, what's this angle? And if this is 30, what's this angle? 30, right? So we translate that. So B is 30 degrees from the horizontal. A is 60 degrees from the horizontal. And we know that the y component of those two vectors has to equal what? And we know that the summed x component of those vectors has to equal what? What's that?
0.
Has to equal 0. Why does the sum, right, the way this guy pulls and the way this guy pulls has to equal 0. Why? It's because we're not moving, right? You tired of hearing that yet? Yeah. All right. So this is our free body diagram that we just drew. Okay, so now walk me through how we would go through solving this. We don't actually have to solve it, right? But walk me through how we'd solve this. Andrew, where do you start?
I would start with, well, obviously the summation of the y components is 20.
Mm-hmm.
The magnitude of this. And then multiply, well, yeah, you can take the sine 30 times magnitude b. And then, it's a really good question. Finding the, oh, wait, it's a different one.
Yeah, that's all right. That's all right. We'll get there. All right. So, like we've been talking about already, Statics is the study of things in equilibrium. Net force has to equal 0, which means that the net force in all directions has to equal. So what does the force in the y direction have to equal? What does the force in the x direction have to equal? What does the force in the z direction have to equal? 0, right? All right, so we're in our three-dimensional space. Okay, everything has to equal 0. And this is the foundational concept of statics. Okay, if it's moving, it's dynamics, and we don't like it, right? Or at least for the moment. All right, so like I said, this is our fundamental statics problem. So we're going to look at the x components here, the y components here, and then we just do our component balances, right? We know that the sum of x has to equal 0. We know that the sum of y has to equal 0. Okay? So in this case, in the case we were looking at before, what we do is we know that 0 has to, we know that cosine here, right? So this is a, so we know that the cosine of a has to sorry, I got off. What I'm saying is, because we know that the force equals 0, that means that the cosine of a has to equal the cosine of b, right? Because you're actually subtracting them too. So that even makes it convenient. You don't have to deal with those dirty, dirty negative sides, right? And then in this case, the y component balance now, we have the sine of theta a, sine of theta b, but we also now have to subtract the weight. So we bring the weight to the other side and we get sine a, sine b equals w. But remember, we're multiplying here by variables. We have a cosine theta, b cosine theta, a sine theta, b sine theta. And what can we start doing? We can start doing plug and play, right? All you have, once you solve, it's just like a system of equations that you guys have done plenty of times in math. Once you have two equations and you have multiple unknowns, you just go through, you solve for one of them, you substitute it in, boom, the whole problem gets solved. Nice and simple, easy peasy. Okay, any questions on that before we move on? All right, so let's talk real quick about engineering structures, because that's fundamentally what we actually care about. So what do you guys think I mean when I say an engineering structure? What do you think?
Structures that engineers commonly use.
Okay, is a building an engineering structure?
Could be.
Could be. Is a bridge an engineering structure? How about a crane? How about your desk? Yeah, your desk is an engineering structure, right? It's something that's been built to perform a function. Okay? So when we think about engineering structures, we think about the super sexy stuff, right? Super tall skyscrapers, cranes. Cranes are actually one of the more fun ones to play with because they have to be counterbalanced and all sorts of bad things can happen, right? But anything like an airplane wing is a great example. Tons of engineering hours go into designing the perfect airplane wing, right? Then think about it. It's flying through the air. It's under multiple forces from multiple directions, and it has to be able to perform a function, right? That's actually a perfect scientific example of an engineering structure. Okay, construction crane, and even a prosthetic leg, right? Our BMEs in here thinking, oh, I don't need to know this because I'm going to go play with cells and cure cancer, right? If you want to go into prosthetics, we actually had a student 2 years ago who was dead set on going and doing prosthetics, right? Think about it. Your body is putting forces on that, has reaction forces. If you decide to run with it or something like that, there's a ton of engineering that goes into something like that as well. Okay? And that brings us to structural analysis. So structural components. So let's look at this really simple engineering structure that I have here. Right? This is just a triangle, but it's what we call a three-member object. So structural components, called elements or members, are the basic building blocks of the structure. So in this case, we have the bar at the bottom, then we have the two bars in the triangle. Why do I have to have a bar on the bottom, first off? What would happen if I applied a load to the tip of that triangle? It'd fall out, right? So if I got, well, that's not quite great, but so if I have this, what happens when I put here? It just goes like that, right? Falls apart, nothing holding it. So from an engineering standpoint, we put something here to hold it all together, right? Super easy, makes sense. Okay? So each one of these, when this load, and everybody knows what I mean by a load, right? A force, applied force is a load. Okay, so when I apply a load to the tip of this structure, the force is transmitted downward here, and the force is also carried by this bottom member. And what also? The ground, right? The ground has to push back in equal and opposite, right? Otherwise, what would happen to our poor structure? Go into the ground, get crushed, it'd fall, right? All right. So if we go in and we do our structural analysis on it, what does this thing right here, which is a drawing of the structural analysis, what do we start seeing a whole bunch of? Vectors, right? Component vector. Well, these aren't component vectors yet, but we're actually looking at vectors. We're using vectors to describe the various forces that are being transmitted within the structure itself, within the members that are on it within the structure. And this makes sense, right? If the load's going this direction, this member right here, is it under compression or tension? Why? It's being pushed, it's being pressed, it's being squished, right? What about the guy on the bottom? Is he under compression or tension? Why? So he's being pulled apart, right? So these guys, so you have a force pushing downwards here from the load. You have a reaction force here that's pushing upward. And then you have a transmitted force within the bottom guy. Okay? So yes, we already got there, but tension, right? These are the forces that act on a structure. There are 4 basic types of forces. So tension, the first one, is deformation, which lengthens an object and narrows it. Okay, so it'd be like taking, I should have silly putty actually, right? You take your silly putty, you pull on it, what happens? As long as you don't go like this. If you pull it slowly, it'll stretch, it'll get super, super, super thin in the middle, and eventually it'll pop under its own weight, right? On the flip side, we have compression, which you guys just talked about, which is if something squishes, right? And again, we are talking about rigid-ish bodies at this point, right? But if we press on, let's say again, let's use my example of silly putty. If I press on my silly putty, it maintains the same total volume. So if it gets shorter, what has to happen to it? It gets fatter, right? If I pull my silly putty apart, it has to get thinner because we made it longer. It has to get thinner. It has to maintain the same volume. Okay. We also then have, and these ones are a little harder to understand, but we have shearing. Shearing is if I have forces acting on it in a different direction, something like this. Does that make sense? Right. So what's happening is on the top, and it doesn't have to be 2 forces in the same direction. It could be just moving my hand across the table. Right? I'm applying a force in one direction. In order for that not to move, what has to happen? There has to be an equal and opposite in the other direction. So what you're basically seeing are the layers of molecules within that being drug apart. Does that make sense, everyone? Okay, perfect. Then we have torsion. So torsion is a special case of shearing. And the best example I can come up with here is like if you're screwing something in. Right? If you think about if you're screwing an object, if you're screwing a screw in, right? Screwing a screw into a board. Think about the forces that are actually being applied to that screw. It's in a round fashion, we can all agree on that, but it's also, right, the screw itself doesn't want to go into the board. The board's pushing back, and you're trying to make it go in a certain direction, right? Which means that on the top, it's being pulled in this way, on the bottom, it's being pulled in this way, right? So you have a shearing that's happening, going in different directions, okay? So those are the 4 basic forces. Do I have any questions on this? The first 2 are super easy. Right? Do I have any question on shearing? Shearing, unfortunately, happens a lot in engineering structures. Torsion, less so, but obviously in the case that I used, it does. Okay? So, what we're going to talk about here, and hopefully this picture does it justice, but bending is a thing that happens to most engineering structures. Okay? If I have a load that's pushing down, like let's say, I don't know, on a bridge, right? If I just have one member within that bridge, or within, let's just say we have a log bridge, okay? Make it super easy. We took a 2x4, we laid it across the river because we laid it across the creek because we had to get to school, right? As you're walking over that, we all know that it bends. Bending is a super cool case of material deformation because what happens is the top of that material is actually under compression. Right? Because as you think about it, the top is actually being pressed onto each other. But the bottom now, because it gets longer on the bottom, it's actually, the material itself is actually under tension. It's actually starting to tear itself apart. So let me ask you a question. what do you think, Vikram? If this material were to fail, where do you think it would fail first? In the middle? Why?
Because if you have your applied load in the middle, I guess that's like the weakest point where the supports are further away.
Yeah, no, I mean, so I agree. So now let me ask you question advanced number 2. If my material, so we agree it's going to fail in the middle, right? That one's pretty self-explanatory, and I agree, and well done. Is it going to fail on this side, or is it going to fail on this side of the material? What do you think? And why? It'll fail on the bottom?
Yeah.
You're correct. Right? 9 times, like, it's probably more than that. It's probably like 99 times out of 100, materials will fail more under tension than they will under compression, right? A great example of that is concrete, right? What do you see when you walk on concrete all the time? Cracks. You see cracks in concrete. Why do we see cracks in concrete? Do you know? You're nodding. Do you know why we see cracks in concrete? Well, from the tension. Yeah, I mean, fair enough. Yeah, but what happens, like, you guys step on concrete all day long, right? You can jump on it, pound on it, nothing happens to it. Concrete is fantastic at absorbing compression. But as soon as it gets cold, actually, it gets hot, it expands, right? When it gets hot, it expands, starts pressing on other things. When it gets cold, it's in tension, it starts pulling in on itself. And that's why, like, when you guys are going over the bridge, like the Fremont Bridge, I'm assuming you guys have all driven over that at some point. What do you feel when you're going over that bridge? You feel chunk, chunk, chunk. What are those chunks? Does anybody know?
To allow it to.
Yeah, expansion joints. Yeah, it's because what happens if we don't give it any room when it expands? Presses on each other and you get cracks, right? So that's why you're going to see it. That's why concrete is not poured in one slab. That's why you see generally like 3-foot squares of concrete, sometimes 4-foot squares of concrete. It's to give it kind of room to expand. But you still see concrete cracks because it can't handle tension very well, right? And when you typically see it crack, what will happen is it'll either fall in, which would be the opposite case here, right? You'd see it fall in and it would crack from the top, or you'll have something like a root come up from underneath, press it, and then it bends again, and you see it crack in that fashion. Make sense? Okay. All right, so yes, this causes the beam to bend. The top edge is squeezed together, and the bottom edge is stretched. All right, so now let's talk about real quick the strength of shapes. Does anybody know what the strongest shape is? Triangle, everybody knows that one, right? You guys learned that one probably in like grade school. All right, but I want to talk about it from an engineering standpoint. So when we look closely at structures, we can see the elements are arranged into various things, right? If we look around here, what's the one we see most commonly just looking around this room? Rectangles, squares, parallelograms, right? And why is that? It's because unless you're a hobbit, circle doors don't make a ton of sense, right? You guys, come on. You guys look at me like I'm a crazy person. You guys have seen the movie, right? At least read the books. They have circle doors. Go to New Zealand. All right, fair enough. All right. So if we have, in this case, our rectangle here, okay, even a small, so remember, when we're talking about the strength of an engineering structure, we're talking about the individual members, right? If I have 4, let's say that this square here is 4 steel beams put together in that arrangement. And they're screwed together, no problem. Maybe they're even welded together, no problem. Okay? To make that individual component fail, you have to put a ton of weight on it, a ton of a load on it, or do something significant to make that individual member fail. However, even though the individual member fails, the structure itself can still fail. And the example of that is here in this square. If I have a square like this, like say of our 4 steel bars, and I just push on it, all that has to break is one of the welds, right? All of these members, in this case, this blue line, exactly the same length as this blue line, exactly the same length as this blue line, exactly the same length as this. None of our members, none of our structural members have broken. None of our structural members have deformed. We haven't had to deal with the material properties of those at all. And we'll be talking about material properties much later in the semester. But fundamentally, we haven't had to do anything to those members. They haven't broken, they haven't failed. Okay? So our material design can be solid, while our engineering design is not solid in this case. Okay? So, as you guys said properly, triangle is the only shape that does not have this same problem. right? You cannot deform a triangle without breaking one of its members. Does anybody know why? What do you think? Okay, fair enough. So all other shapes can be deformed because their angles aren't fixed, right? If you look at a triangle, the length of one side can be determined by what? The other angle. Well, the other two, but those two form an angle, right? So side A and side B are some length, and then side C is some length, and based on the length of side C, it forms an angle of A and B, right? No matter what you call A, B, and C, any way around the triangle, the angle between two members is determined by the length of the third member, right? So the only way to change that angle would be to do what to the third member? Make it longer, make it shorter, break it, blow it up, whatever, right? So that's functionally why your triangle is your strongest shape, is because the triangle functionally becomes just as strong as any individual member, right? So if you make it out of steel, make it out of toothpicks, make it out of whatever, you have to break the member in order to break the shape. It's the only shape that works like that, right? Like we already saw with the square could maintain all the members the same and it can still tip over. Any parallelogram or whatever you want to come up with, the same. It can move without actually changing the member. So by using the triangle, it becomes just as strong as the material that's used to build this triangle, okay? However, we can solve this, and you guys probably did this in grade school also, but we can solve this by adding what we call a reinforcement member. In this case, it's called a brace, okay? So this is a reinforcement component which adds strength to the structure, but fundamentally, what did we just do to the square? Made it two triangles, right? It's the same idea, okay? But again, it doesn't make sense to have triangle doors and stuff like that. A lot of our buildings would be really sad if they all looked like triangles, right? So functionally what we can do is we can make our squares, make our rectangles, whatever, and make sure that they're reinforced, okay? So a brace, by the this is not gonna, you're not gonna get tested on this, but a brace that is under compression is actually called a strut, right? So you may have heard braces, struts, ties, stuff like that, right? So a brace that's under compression is called a strut, and a brace that, compression is a strut. So if the bridge, if you're like on the bottom side of a bridge and it's getting pressed on, that would be a strut. Something getting pulled apart under tension would be a tie. And you'll hear those used interchangeably, and again, this is not a test. All right, so now I believe this one is on page 10, if I'm correct. Nope, I am wrong. It is on page 13. So this one should be real quick. Please draw in struts and or ties on the shapes below in a way that will keep them from collapsing. I'll give you 30 seconds. All right, we all ready? All right, Eva, what do you have for the triangle? You skip the triangle? That's smart, because we don't need to do anything to the triangle. So, because that's all we need to do is make triangles. All right, what do you have for the square?
Just one going through.
Just one brace? I agree. What did we get for the pentagon? What's that? Two braces? How'd you do it, Tom? Bottom left corner? Okay, so I did them from the top, but you could just spin it, right? So I agree. I think it's just two braces. All right, how about the hexagon? What'd you do for the hexagon? You did three? How'd you do them? 1, 2, do they all cross in the middle? 1, 2, 3, okay. So that's the way I did it, but you could certainly do it from, you could all make them cross, and then you'd have six natural triangles. All right, simple enough. We're all civil engineers now. Gonna go build a bridge, stamp it, perfect. All right, so what we're gonna be doing for our lab tonight, we're gonna be playing with bridges, be playing with trusses. So an engineering application of this is the truss. This should not become as a surprise to you. Everyone's seen bridges like this, I'm sure. So a truss is a special kind of engineering structure composed of straight members connected at their ends, and they're connected with what we in the engineering world called a pin joint. Functionally, so in theory, the pin joint is allowed to rotate freely. That's how we do it from an engineering model standpoint, because the idea is that your structure should not be able to, if you design it right, it should not be able to move, okay? Now functionally, we're not going to build a bridge with a free rotating thing, right? weld it, we rivet it together, right? We all get that. But functionally, from a design standpoint, each one of these, we think to our head, can move on its own. It can rotate, and the members can rotate around those points. And again, the idea is as long as we build our structure correctly, it will be stable enough that it won't be able to rotate. Because again, we all agree that the members are the strongest part. Where is our weakest part? The weld, the rivets, right? You've got these huge pieces of metal being held together by like 4 screws. That's crazy town, right? It needs to be designed such that you're not putting stress on the screws or on the weld. Okay? Does that make sense? So the truss design takes advantage of the stability of the triangle, and that's all we're doing here, right? We've got a couple members on the bottom. This is called a Warren truss, by the way. That'll also be on the test later. Again, we've got our pin joints, but all we're doing is we're just making a series of triangles. Okay? When designed correctly, these things can carry an intense amount of weight. Okay? So, a bridge structure constructed with an unbraced quad at the center, like this, is able to deform under an applied load. Because what happens? These triangles stay the same, but the middle can actually bend. Right? So that would be a very sad bridge. You would not want to be the guy in the truck crossing that bridge because it could deform and all of a sudden you're stuck in the middle. Okay? Instead, obviously, if we just throw a strut in there, we can now lock it and it will not be able to move because it's nothing but what? Nothing but triangles. Very good. Okay? So that is the end of the lecture. Please come back in like 5 minutes. I will we'll form groups and then we'll play with our bridges. So I'll see you guys in 5 minutes. Thank you for watching Introduction to Basic Concepts in Engineering. Has this piqued your interest and you want to learn more? Much of the course content and the images in this course are from the text Introduction to Basic Concepts in Engineering for Adept High School Students by Andrew S. Heinz, PhD. While the textbook is not essential to successfully follow all class videos, it is an excellent resource designed specifically for introducing a student considering engineering to the field and for preparing them for the next steps. It contains many additional topics not presented due to time constraints, as well as additional practice problems and answers. The full text is also available on Amazon. Also, find us on Facebook at SHS Intro to Engineering.